Section 11.11 Applications of Taylor Polynomials. Previously, we found Taylor series to represent different functions, and then we showed that those Taylor series would have to be equal to those functions, but in general, that's kind of hard to find an entire Taylor series equal to a function. What's a little bit easier often is to approximate a function using a Taylor polynomial, which means we just cut off the Taylor series somewhere. So, for example, let's say I had y equals e to the x. We already know what the Taylor series for e to the x is, but let's say we didn't. Well, then I would draw, say, here's e to the x, and how about I label that? And what I could do is say that the polynomial t1 of x, which is the first part of the Taylor series, so that's f of a plus f prime of a over 1 factorial times x minus a. And then if I wanted to continue the Taylor series, I would keep writing terms with x squared, x cubed, etc. But I only want the first degree Taylor polynomial so far. Notice that at a, let's say I put a at, how about over here at 0, 1. Then at a, t1 of x is just the linearization of a. It's just the tangent line approximation. So how about I use, I don't know, I could use green for that. So then this would be t1. So here's y equals t1 of x. And you'll notice that if you look near a, then the function is a pretty good approximation, or t1 is a pretty good approximation for the function y equals e to the x, but when you go farther away, it becomes a very bad approximation. So this was if t was equal to 1, but what if I went and did a different Taylor polynomial? Let's say I go to t2 now. So let's see. I'll use a bit orange for that. So the second degree Taylor polynomial would be if I went 1 degree more. So I'll go to f double prime over 2 factorial times x minus a squared. So then it looks like I'll get a parabola because I have a squared term. So it would look something like this. If I was using second degree Taylor polynomial to do my approximation, so that would be y equals t2 of x. And then if I wanted a third degree, it's always so hard for me to decide what color I want. Let's change this to 3. And we'll throw in f triple prime at a over 3 factorial times x minus a cubed. So I get a nice cubic, which looks something like this. Okay, so you can see that the cubic is the closest we've gotten so far. It's pretty close almost all the way around. I mean, eventually it gets farther away, like over here, but even over here it's closer than it was before with the square or with the linear function. So this is y equals t3 of x. And as you can see, the higher the degree of the Taylor polynomials, in general, the better approximation you get for your actual function. You just keep doing more and more degrees and adding more and more terms to your Taylor polynomial if you want a better and better approximation. So let's do an example of this, and how about we approximate the function f of x equals the cube root of x by a Taylor polynomial of degree 2 at a equals 8. So in order to do a degree 2 polynomial, we will need to find the second derivative, and the first, but we'll have to at least go to the second. So we'll write f of x equals cube root of x. That's x to the 1/3, which will help us take the derivative. And we know that f of 8 is 2. So f prime prime of x using x to the 1/3, and the power rule is 1/3 times x to the minus 2/3. So f prime of 8 is 1/12. And then f double prime of x is equal to minus 2/9 times x to the minus 5/3. So f double prime of 8 is equal to 1/144. And we're going to need the third derivative for the second part of this question to see how accurate the approximation is, because you need the next derivative to either use Taylor's inequality or the alternating series estimation theorem. So let's just compute that, even though we don't need it to write out our series, because we only are going into degree 2. So the third derivative is 10/27 times x to the minus 8/3. So that means that our second degree Taylor polynomial will just be our series stopping at the second degree. So that's f of 8 plus f prime of 8 over 1 factorial times x minus 8 plus f double prime of 8 over 2 factorial times x minus 8 squared, which is equal to 2 plus 1/12 times x minus 8 minus 1/288 times x minus 8 squared. So that means that we can approximate the cube root of x using our second degree Taylor polynomial, which we found is 2 plus 1/12 times x minus 8 minus 1/288 times x minus 8 squared. Let's see how accurate this approximation is when x is between 7 and 9. So we've got our Taylor's inequality. Notice that we can't use our alternating series estimation theorem in this case because our series is positive, it's not alternating. So we'll use Taylor's inequality, and we've got that our remainder is less than or equal to m over 3 factorial times x minus 8 cubed. So we need to find out what m is, and we need some sort of bound on x minus 8 cubed. So we know that x is greater than or equal to 7. So that implies that x to the 8/3 is greater than or equal to 7 to the 8/3. So our second derivative, which is 10/27 times 1/x to the 8/3, will be less than or equal to 10/27 times 1/7 to the 8/3. Notice that I went with the x being greater than or equal to 7 part of the inequality when trying to choose m, because I knew that I would have to divide by it, and when we divide it, that'll flip the inequality, so that'll give me the less than that I want. So now I know that this is going to be less than 0.0021. So this means that I should choose m to be equal to 0.0021, and now I have an estimate on our second derivative. Let's find an estimate in x minus 8 cubed now with the absolute value. So we know again that x is between 7 and 9, so we can subtract 8 from every side. So we get x minus 8 is between 1 and minus 1. So that means that the absolute value of x minus 8 is less than or equal to 1. So now we have enough information to plug into our remainder estimate, and we see that that's less than or equal to 0.0021 over 3 factorial times 1 cubed, which is 0.0021 over 6, which is less than 0.0004. So we are accurate to within 0.0040. I think I need to say another 0. What is the maximum error possible in using the approximation sine of x approximated by, it looks like, the first 3 terms of the Taylor polynomial? So, or the Taylor series to make the Taylor polynomial, when x is between minus 0.3 and 0.3. And then we'll use the approximation to find sine of 12 degrees, correct to 6 decimal places. So we're looking at the remainder after 3. Notice that this series is alternating positive, negative, positive because it's sine. So that's kind of wonderful. We can use our alternating series estimation theorem instead of using Taylor. So we don't have to find m, we can just look at the first omitted term. So the first omitted term, and it needs to be positive, we take it without the sign. So we'll have to take the absolute value of x to the 7th over 7, just the first term that doesn't appear here. So that's the absolute value of x to the 7th over 50/40. Okay, now we know that minus 0.3 is less than or equal to x, which is less than or equal to 0.3. So that means that absolute value of x is less than or equal to 0.3. So now we know that our remainder is going to be less than or equal to 0.3 to the 7th over 50/40, which is about 4.3 times 10 to the minus 8. So we'll definitely be correct to 6 decimal places. We're even past that. So let's get the sine of 12 degrees now. So in order to get the sine of 12 degrees, remember you have to be very careful using derivatives when it comes to degrees, because the derivative of sine in degrees is not cosine. So the Taylor series for sine in degrees is not what we calculated before, and the Taylor polynomial won't approximate sine in degrees. So we need to convert to radians first, or find another formula, which will take longer. So sine of 12 degrees is the sine of 12 times pi over 180, which is just the sine of pi over 15. Okay, so now that's approximately pi over 15 minus pi over 15 cubed times 1 over 3 factorial plus pi over 15 to the 5th. Almost forgot my 1 over 5 factorial over here. So that's approximately 0.2079169. So we could say that the sine of 12 degrees is about 0.207912. Correct, just 6 decimal places. Okay, how about values of x for this approximation to be accurate within 0.00005? Well, for our remainder estimate, we know that's less than or equal to absolute value of x to the 7th over 50/40, which is less than 0.00005. So we need to, when I say it's less than, I mean we're going to set it less than, and we're going to find values of x that make this work. So we're solving this. We see that we need this thing to be less than 0.252 when we multiply both sides by 50/40. And then we solve for absolute value of x. We get that that's going to be less than 0.252 to the 1/7, which is about 0.821. So it looks like it'll be as accurate as they want when absolute value of x is less than 0.82. So if we were to draw what's going on here, then let's say here's sine. Let's see if I can actually do it. Yeah, whatever, good enough. I'll get the loop a little bit small over here, but that's okay. So we're going to approximate this, how about with t1? So that would be a linear function, so approximate something like this. So notice that near 0, that's a great approximation, it's roughly linear, but when you go farther out, or even farther out, it becomes terrible as an approximation for sine. But if we then went to, let's say, t3 for our third degree Taylor approximation, then that's a nice cubic. Let's see if I can draw that. It's like something like this. So this cubic t3 is a little bit better than our first degree Taylor polynomial. If we then get, how about an even better approximation? Let's say t5. See if I can draw that. Oh. I don't like how it curled up at the end. I almost got that one. Okay, so that's like roughly what the fifth degree Taylor approximation for sine would look like. So then, I could even keep going though. How about, let's say seventh degree. Maybe I chose a color a little bit too dark, I don't know. So you can see that the seventh degree one, well, I didn't draw it very well on the other side. Here, try to fix that. Looks something like that. This is the seventh degree Taylor approximation, and it almost hugs the function perfectly until we get to a certain point. So the better and better, well, the more and more terms you put in your Taylor polynomial, the more and more kind of potential loops that you can have to go up and down. I don't know about loops, not the best word, but you can kind of hug the curve sine more and more and more the more terms you add to it and get a better approximation, which is kind of cool. So we only did ours for that T3, but, or actually ours is, sorry, ours is fifth degree. So ours is the T5 one that we drew. So it's pretty bad over here, but near 0, it's great. So this was, oh, I forgot to label it, y equals sine of x. Okay, let's do one more example. In Einstein's theory of special relativity, the mass of an object moving with velocity v is this thing, m equals m naught over square root of 1 minus v squared over c squared, where m naught is the mass of an object when at rest and c is the speed of light. The kinetic energy of the object is the difference between its total energy and its energy at rest. So the kinetic energy k is mc squared minus m naught c squared, or m0 c squared. Show that when v is very small compared with c, this expression for k agrees with classical Newtonian physics. In other words, k equals half m naught v squared. So we'll write k equal to mc squared minus m naught c squared. And then we'll plug in, because we know what m is. So we have m naught c squared over square root of 1 minus v squared over c squared. And then we subtract m naught times c squared. So factoring out, we get that that's m naught times c squared times 1 minus v squared over c squared to the minus 1/2 power minus 1. Okay, so it looks like this thing is the mess that we have to get rid of to somehow show that this thing will agree with this. So we should probably approximate this using a binomial series. So we'll use the binomial series 1 plus x to the minus 1/2, and we'll just replace x with v squared over c squared, or minus v squared over c squared. So let's write out the binomial series for 1 plus x to the minus 1/2. That's 1 minus 1/2 x plus minus 1/2 times minus 3 over 2 over 2 factorial times x squared plus minus 1/2 times minus 3 over 2 times minus 5 over 2 over 3 factorial times x cubed. We're just writing out the Maclaurin series, and so on. So that ends up becoming 1 minus 1/2 x plus 3/8 x squared minus 5/16 x cubed, and so on. So how about we now substitute in? We know that k is equal to m naught c squared times this series minus 1. So we will plug in for x, where x is going to be minus v squared over c squared, so our first minus becomes a plus. So we get half v squared over c squared plus 3/8 times v to the 4th over c to the 4th plus 5/16 times v to the 6th over c to the 6th, and so on, minus 1. And then you might be thinking, wow, that's terrible, but did you notice that the 1 cancels? So we just get half v squared over c squared plus 3/8 v to the 4th over c to the 4th plus 5/16 v to the 6th over c to the 6th, and so on. So that means that k is approximately m naught c squared times half v squared over c squared, because if this value over here, v squared over c squared, is very small, then when we square it again, it'll become really, really, really small. So these terms we could think of as being roughly negligible. So we'll leave those out to do our approximation and just get half of, well, let's see, the c's cancel. So it's just half of m naught v squared, which is exactly what we wanted to show, that when v is very small compared to c, that's what happens. Okay, let's now see how bad of an estimate this is. So when the absolute value of v is less than or equal to 100. So we did a first degree Taylor polynomial. Oops. Okay, no idea what happened there. So that's going to be less than or equal to m over 2 factorial times x squared. We don't need the absolute value because we're squaring x, so it's going to be positive anyway. So f of x is m naught times c squared times 1 plus x to the minus 1 over 2 minus 1 I forgot my parentheses. Gotta put that right over there. Okay, that's better. And x is minus v squared over c squared. So we're looking for the second derivative for our m. So the second derivative is 3 over 4 times m naught c squared times 1 plus x to the minus 5 over 2. Just do the, I mean, it's chain rule, but it's really just the power rule because taking the derivative of x is just 1 anyway. Let's do that twice. And then you get the absolute value of v is less than or equal to 100 meters per second. So now we can say that the absolute value of the second derivative will be 3 times m naught c squared over 4 times 1 minus v squared over c squared to the 5 over 2. And that'll be less than or equal to 3 times m naught c squared over 4 times 1 minus 100 squared over c squared to the 5 over 2. Notice that you have this thing less than or equal to 100, so we just slip that right in there. And we'll choose this to be equal to n, because that's our bound in our derivative. So we also know that the speed of light c is equal to 3 times 10 to the 8th meters per second. So we'll plug that in too. So we get that our error is less than or equal to 1/2 times 3 m naught c squared over 4 times 1 minus 100 squared over c squared to the 5 over 2. And we need to, no, almost forgot, we need to multiply by our estimate over here in order to find our error. All we did was find m. Okay, well, we know that x is minus v squared over c squared, and v is less than or equal to 100. So to square this, that means we're looking at v to the 4th. It will be less than or equal to 100 to the 4th over c to the 4th. And then plugging in c equals 3 times 10 to the 8th, we get that this is less than 4.17 times 10 to the minus 10 times m naught. So that means that the difference between our expressions for k is at most 4.2 times 10 to the minus 10th, which is kind of cool because it's just a first degree Taylor polynomial. So we might have expected it to have a much higher degree of error, but it actually wasn't that bad.